Well, here's Wave Optics Part 2. Part 1 was interference, and we saw various examples of that. Part 2 is a different phenomenon, diffraction. It's in the textbook, Chapter 34, Section 3. Here are some quotations from the textbook. Any wave passing through an opening experiences diffraction. That's the first sentence in this section. The second sentence is, diffraction means that the wave spreads out on the other side of the opening rather than the opening casting a sharp shadow. So in other words, the question is, if you have, let's say, an opening and some waves approaching the opening, and this region is opaque, but there's a hole, what will you see on the other side of the screen? So this is sort of a top view. You have a screen here, which is like something opaque, like a metal foil. And then in that foil, there's a slit. It's been cut out with a razor blade. So this is like a front view, and this is the top view. And now what will you see over here? Well, if these were particles and not waves, what you would see over here would be a shadow. The light would only come through the region of the opening. And it would be dark above and below the region of the opening. So in other words, if you were standing right here and looking towards the hole, you would see nothing. But that's not what happens, because light is not a stream of particles. So this is all wrong. What happens is that there will be waves traveling away from the hole in all directions, well, except for backwards. But in these directions, there will be waves spreading out, traveling away from the hole in the screen. That's what's observed. As long as the size of the opening is comparable to the wavelength or less than the wavelength. If the size of the hole is much larger than a wavelength of light, then there'll be a shadow. It won't be a perfect shadow, as if these were a stream of particles, but there will be, most of the light will come off in the direction through the hole. That's for the case of where the wavelength is small compared to the hole. But if the wavelength and the size of the slit are similar, or the wavelength is larger, then you have this diffraction. Diffraction happens in both cases, but it's more pronounced if the wavelength is small. large. Compared to what? Compared to the size of the opening. Now, there's another sentence I'll quote. Huygens' principle describes this spreading out. So let's consider the case of single slit diffraction, which is what I have here. There's one parameter in the problem, namely the width of the slit. If I blow this up a little bit, A, that's the one parameter in the problem. Well, also the wavelength lambda is a parameter in the problem, but that's not really adjustable. I mean, the wavelength is the wavelength of whatever light you have. So the wavelength isn't really variable, but the size of the slit could be varied. And according to Huygens' principle, if you think, the propagation of the wave occurs in such a way that you could assume that at any point on a wavefront, that acts as a little source of wavelets. So for any of the points inside the slit, it acts as a source of wavelets. And so you have, well, this sort of imaginary dividing the slit up into about 5 parts. You'd have the superpositions of the wavelets from 5 different parts. And the result would be outgoing circular waves. Now, to make this quantitative, since this is just a qualitative picture, you can look at figure 25, which shows plane waves approaching a slit whose width is, let me blow this up a little bit, whose width is A, and divided up into 2 parts, A over 2 above the center and A over 2 below the center, and look at the outgoing wavelets of Huygens' principle, and then project the light onto a projection screen down here. Well, depending on the angle, at a point on the screen, you may get constructive interference or destructive interference. See, what happens is the distance from this point on the opening to the point on the screen, and the distance from this point to the point on the screen is different. So there's a phase difference between the waves from these 2 different points. Now, of course, you don't have just those points. You have all the points in the slit, but different parts of the slit may interfere constructively and destructively, so that the point on the screen could be bright or dark. So, as the book says, this is the geometry for determining the location of the first dark fringe from a single slit, where the slit size is A, using 2 rays from the slit. And the analysis of that leads to an equation. And I'll write down the equations. I won't go through the analysis here in the screencast. This is better if you read about it in the textbook. The result is equation 15, or there's a little more to be said about this, so a series of equations. Equation 15 says that the first dark fringe, the first region where the destructive interference occurs, so that the intensity is 0, occurs at this angle theta, so this is the angle theta, where A sine theta is m lambda, and m is an integer. So M can be 0, plus minus 1, plus minus 2. So you get a series of dark regions. Theta equals 0 is a dark region because there's destructive interference from the waves above the center line and below the center line. And then you get fringes. You get regions of dark or destructive interference. And between those regions of destructive interference, you have regions of constructive interference. Okay, so on the screen here, on the projection screen, you have an interference pattern. And there'll be alternating bright and dark fringes. And this is the equation for the destructive interference. Now, to get the full intensity pattern, you have to carry the calculation a little further. That's given in the book. And this is the intensity as a function of angle for for an arbitrary angle. These are just the special angles where you have destructive interference. But what if you wanted to know the intensity at every angle? Well, that's this equation. That's equation, I think it's equation actually 17. So if you're asked to calculate the intensity at a particular angle, you would have to use this equation. And it depends on a quantity alpha, which I think is equation 18. 18 gives the equation for alpha, which depends on theta. Depends on theta and the other parameters in the problem, namely the slit width and the wavelength and the angle and things like that. Also the distance to the screen. So actually, for this kind of experiment, there are a number of different parameters that all kind of conspire together to give you this formula. Now, moving ahead in the chapter 34, there's a section on diffraction by a circular opening. So here's a little, here's the result of a Google search on diffraction by a circular opening. It's from some hyperphysics website. Shows various things. What you have here is light coming in. There's a opaque material here, like a piece of metal, but with a hole in it. And now the light goes through the hole. But it spreads out because of diffraction. So the light is then projected onto a projection screen here. And you get a diffraction pattern. You get rings of bright regions and dark regions. So the diffraction pattern here is a set of concentric rings. Here's a plot of the intensity as a function of radius. Let's say y. Let's say you take the vertical direction and measure the radius from the center. So here's the center where you'd have the highest intensity, and then you have a region of low intensity, and then a region of high intensity, and another low intensity, another high intensity, another low intensity. So in other words, you get fringes, you get alternating regions of high intensity and low intensity. This equation, sine theta, is m lambda over d. M can be 1, 2, 3, and so on. And these are the values for minimum intensity and maximum intensity. You get the largest intensity at around theta equals 0. And there's a big central region. But then there are these little fringes on the outside where you have alternating high intensity and low intensity. There are various parameters. There's the wavelength of the light, so this is some kind of red light. There's the M value. M is an integer. That's called the index. There's the diameter of the circular opening. So this circular opening has a diameter d. So this is expressed in terms of the diameter, not the radius. So d is the aperture diameter. I think I said something wrong. M is not an integer here. These are the M values. So unlike a slit, you have in which, it's lambda over d times an integer. In the case of circular aperture, it's lambda over d not times an integer, but times a number which might be 1.22 or 2.23 or 3.32 for the minimum or for the minima of intensity. And then in between the minima, there are maxima, 1.65, 2.69, and so on. So the index, it counts which fringe you're talking about. Here's fringe number 1, fringe number 2, fringe number 3. The M value is given by properties of the circular aperture problem. Now, of course, to relate the angle to the position on the projection screen, you have to use trigonometry. You have an angle and you have a height. Well, that gives you a right triangle, and so you can say that the height is d times the tangent of the angle. D times the tangent of the angle. Now, the tangent of the angle is usually small. The angle is usually small, so the tangent of the angle is roughly the same as the sine of the angle, which is roughly the same as the angle in radians. So for small angles, and that would depend on how you set up the experiment, but you usually will have small angles. You can approximate the tangent of theta by theta. All right, so that's the picture. Now, that's not all given in the textbook. What's given in the textbook is this equation. Equation 20, chapter 34. The position of the angular position of the first minimum intensity is 1.22 lambda over d. It's like this. The minima occurs when m is 1.22. Not an integer, but close to the integer 1. Sine theta is 1.22 lambda over d. Now that implies something about optical instruments like telescopes. If you had two sources, if you had two pinholes, or if you had two holes here, then could you tell them apart? since you don't have a perfect shadow, you have instead diffraction, their positions on the projection screen would be overlapping. Could you tell them apart? Well, you could tell them apart if this 1.22 lambda over d was sufficiently large that they could be separated on the screen. So you can tell them apart if the angle obeys what's called the Rayleigh Criterion. So if the angle is greater than the Rayleigh Criterion, the Rayleigh angle, which is the arc sine 1.22 lambda over d. In other words, if you're at a larger angle, the angle between the two sources of light, if the angle between the two sources of light is greater than 1.22 lambda over d, that is to say, if the sine of the angle is greater than 1.22 lambda over d, then the diffraction patterns won't overlap and you can distinguish between the two sources. So the Rayleigh angle is a measure of resolution. You can resolve the two sources if they're far enough apart so that the angle from the telescope or whatever optical device you're looking at these two sources with is larger than the arc sine 1.22 lambda over d. And again, it's that same 1.22 which has to do with the size, this size here, in angular size, of the diffraction pattern. This is something that you'll find in the Lon-Kappa problems. You will have several Lon-Kappa problems in which you have to use the Rayleigh criterion. And don't forget there's an exam coming up. Exam 3 is coming up. And no doubt there will be a question on exam 3. We haven't made up the exam yet, but I would be very surprised if there's not a question on exam 3 about the Rayleigh criterion. So read section in the section on diffraction by a circular opening carefully in the textbook, because you'll need that for the Lon-Kappa assignment, and you'll need to use it on the upcoming exam. But it's a simple thing. The diameter of the optical instrument has to be sufficiently large so that the resolution angle can be smaller than the actual angle between the two objects. All right, so be sure to read about the Rayleigh criterion and make sure you understand that. And you'll get practice on that in the Lon-Kappa assignment. Here's another example. Double slit diffraction. So you have two slits in let's say you have an opaque screen, like a metal foil or something. And in this metal foil, you've cut two openings. There's the first one. And there's the second one. And now you have light passing through these two openings. Now, we already considered this for the case where the openings are very thin slit interference, like Young's experiment, where the size of the slit is small compared to wavelength of light. But suppose these slits are not all that narrow. Then you actually have two parameters. You have the width of a slit, that's the parameter A, and you have the distance between the slits. That distance is D. So you actually have two parameters. And now, look at figure 36 and look at equation 22. That will show you the intensity of a projection onto a projection screen. It's complicated. Here's a copy of a figure from a website. This is the center part of the interference pattern for red light on a double slit. And it's actually a combination of single slit and double slit interference. So you see you have a kind of single slit interference pattern. And you also have a double slit interference pattern where you have interference pattern, a diffraction pattern. Actually, the diffraction pattern comes from the single slit. And this other diffraction pattern comes from the double slit. It's like Young's experiment, two thin slits. So this is the interference pattern that you would have for particular values of the wavelength of the red light, and A, size of the slit, and D, the distance between the two slits. So you get sort of a large bright region and then some smaller bright regions. And then in the large bright region, in each of the other fringes, you have separation of constructive and destructive interference. And the equation for the intensity as a function of angle is given in the book. It's I0 cosine squared beta sine alpha over alpha squared, where alpha and beta are two parameters that can be related to A and D. So you'll have to look up in the book what's the value of beta, what's the value of alpha, but it depends on theta and the relative size of A and D and so on. Now you recognize this part, that's like two-slit interference with thin slits. But you recognize this part, that's like the diffraction pattern for a single wide slit. So you have this combination of both aspects, single slit diffraction and double slit diffraction, single slit interference and double slit interference. We have in section 4, chapter 34, entitled Gratings, or diffraction gratings. This is a case where you have many sources of light. So for example, you could have an opaque screen cut with many slits. So you have many thin slits in an opaque screen, and light incident on that would be called a transmission grating, because the light goes through the screen, through the slits, and then downstream you have a projection screen where you're interested in the intensity of the light. Well, again, you'll get a diffraction pattern. And if we assume that these are thin slits, so assuming the slits are thin slits, I should say thin slits, that is to say, the size of the slit is small compared to the wavelength of the light, then there's really only one parameter that's relevant, and that's the distance between the slits, d. So the distance between these two slits is d, 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 d. And the derivation in the book gives the angle for constructive interference. So this angle, theta, for constructive interference is given by the equation d sine theta is m lambda, where m is an integer, 0, plus minus 1, plus minus 2, and so on. So that's the case of a transmission grating. Now there can also be reflection gratings, where instead of these sources of light coming from the left-hand side, these sources of light come from the right-hand side. In other words, you have, for a reflection grating, you have reflected light reflecting from a large number of grooves that are cut in the let's say piece of metal. So it's a piece of metal or some other material with grooves cut in it. You have incident light coming in. So here are the rays for the incident light coming in to strike the surface. And then outgoing rays, which are reflecting from the grooves in the surface. Well, these will all interfere. So it'll be the same picture, many sources of light separated by some distance d, so many sources of light, and then interfering, and then producing an interference pattern on a screen somewhat downstream. So you'd put the screen in this problem up here. And so you'd get an interference pattern. A good example of this reflection grating is white light hitting the surface of a CD, compact disc player. CD has many grooves cut in the surface to carry the information about the music. Or it could be a DVD where the information is carried for the information in whatever is recorded on the DVD. And so the light reflects from those grooves in the surface, and you know what you see. You see colored light. You see the colors of the rainbow. So white light reflecting from the surface of a CD or a DVD shows the colors of the rainbow. And the reason is because the conditions for constructive interference, d sine theta is m lambda, depends on lambda. So different colors will be reflected at different angles. A white light is a mixture of all the colors. The red light, which is in the white light, will be reflected at one angle. And if you look at the surface at that angle, you'll see red light. But violet light or blue light is reflected at a different angle. So if you look at the surface at a different angle, you'll see the blue light. And so if you're just looking at the CD surface from all directions, you'll see the colors of the rainbow all separated. And this is explained in section in the textbook. And again, there'll be at least one, probably more than one question about gratings on the homework assignment. So that completes the screencasts. And you should now be able to start doing the line kappa problems, although you may have to refer back to the textbook to pick up the appropriate equation for the appropriate problem.